and the session that I'm going to handle today is about essential mathematics for I have been giving sessions today. Okay, so I the uh, material needed, okay, or as essential for large. Okay, so and as you know that maths is a subject that you have to practice and do maths. Okay, we cannot just give a lecture on maths and just you cannot. It is not enough if you just hear it. Okay, so it is better you have to see how it is really applied. Okay, so practice it so with that about background, then I think reading a paper, okay, reading a research article on machine learning or writing a new article or designing a new algorithm will be very easy for you. Okay, so it is with that intention. So this session has been added, and I'm glad that I'm going to share my views, share my experience with you. Okay, so with this, so I'll start presenting my screen, then switch off my camera. So I think screen is visible to you.
Yes, sir.
Okay,
Visible, sir.
okay, okay. Thank you. This is going to be the agenda. Okay. No, I will be taking the basic linear. This is a very mathematical tool for. Okay. So uh,
Sir, Rangarajan, sir, voice is breaking, sir. Voice is not clear.
I think the network connectivity. Actually, I'm using the college. Yeah, is it okay? Can you hear me now?
Now it's okay, sir.
Oh, okay, okay, right, okay. I think the screen is visible now. Is it okay?
Yes, sir.
Okay, okay, okay. Right. Okay, I think now we can start. Actually, there was, I think, now I think, uh, so this is the agenda going to be today, for today, forenoon and afternoon. So, so we'll be first discussing about linear algebra, basics of linear algebra. So actually, this linear algebra is most for machine learning. Then we are going to talk about the matrix theory. Okay, so actually, when you say linear algebra, that includes matrix. Okay, matrix theory, and we are going to discuss about matrix decomposition algorithm. Okay, and the dimensionality reduction problem. Okay, so this is going to cover. Okay, and in the afternoon, the calculus about the convex function. Okay, and we'll see the optimization. Okay, the constraint, both constraint and unconstrained. Optimization will topics are going to be. Okay. So this is the agenda for today. Okay. So if you have any doubts or anything, you can just interrupt and you can ask. Okay, there's no problem. Okay, or we will have some time in the end of the session. Okay, so the forenoon session, so it's going to be from 10 to 12, 12:30. So maybe 15 minutes at the end we can have for question answer. So with this, so in the forenoon also, let's say 11 to, we'll have a 10 minutes in 11:20 or. Okay. So this is the agenda for today, and now I get into the topic. So we have to have an introduction. So what is machine learning? Okay. So first of all, what is machine learning? So nowadays you see that this word has become a buzzword. So almost everybody is talking about machine learning. Okay. Especially AI also, artificial intelligence. So everybody says AI, machine learning, deep learning. So this is the topics that are one can hear. Okay, again and again in all, as well as academia, research, or industry. So why? Because I will let you tell you that AI has been there for a long time. Okay, so AI is there for a long time. Okay, so the research interest of AI, about AI is the weak AI and the strong AI. Strong AI. So the weak AI is what actually we are all talking about. Okay. Say, for example, say image recognition, which is computer language processing, diseases, prediction of weather. Okay, so all these applications are actually we talk about is weak AI. But actually, strong AI is about making how to make computers think. That's actually strong AI. Okay. So there is a separate field that is having its own. People are doing a lot of research. That is how to make computers think. That's what actually our strong AI is make computers humans are doing presently. Some tasks which better, especially recognition. Uh, look at a picture, okay, and you immediately recognize what is that picture is all about. Okay, you hear a sound, you can recognize speech recognition. So all these things come under VPI. Okay, so because we are doing a task, okay, so we are making computer do a task which the human. Okay, when you are studying computer, that computers are known for their speed, versatility, diligence. We say a lot of things, is it not? Computers don't get tired. Okay, accuracy, precision, all these are the advantages of computer. But when you talk about the disadvantages of computer, the computer cannot do certain tasks which humans are doing better. Okay. Like for example, speech recognition or image recognition, activity recognition, or say summarization, text summarization. So all these things computers are not doing in those. To make computer okay like human is what is called the VKI, and that is where we are actually working. Okay, and so here in this slide you see that the traditional programming is all about giving a computer the input data and also the program, and you get the output. So this is the traditional classical view of a computer. Okay, so you give a data and program to a computer, you get the output. Okay, so this is the job of the computer. So now computer does some processing. So the computer will do the processing. So follows certain instructions. So the instructions are given by the program, do the process. But whereas learning, the input computer given input as okay, given input as well as label output label, and the computer will hardware a program. It will start creating a program. Okay, uh, so from the input and the output will start creating a program. I mean that it will start guessing a function. So what is that function is all about? Okay, so you know that you are giving input output data. So you are giving a pair of values xi, yi. So the computer will go for I is equal to 1, 2. So of paired labels. So input and this is output. So now computer will look at this input output trend, and what it will do is it will try to guess the function what is y of f of x is. It will try to guess the function f of x. X is the input. It will try to guess the function f. Okay, and after trying to guess the function x, give a new data, then the computer will give the new output. For example, the new data is x dash. Suppose the computer guesses the function, then you give the new data x dash, then the same function will apply on x dash, and you get a y dash. Okay, so this is your test output. Okay, so this is what is machine learning is all about. Okay, so implicit programming. It is here. It is explicitly a program. You explicitly tell the program what to do. You tell the program. You tell the computer what to do. Instruction by instruction. There's no ambiguity at all. Okay, but whereas here, with the help of input data and output label, the computer is able to guess a function and apply that function to future values. So this is what actually is all about in machine learning. So this is what you call machine learning, and machine learning is actually comes under the broad umbrella of AI. Okay, machine learning is learning from data. So I will say learning from data. So when we say so again types, so you know supervised learning, unsupervised learning, then you know what is reinforced learning. So these are the learning algorithms that come under machine learning. So the what example I have given here is an example of supervised learning. Why supervised? Because you give the input and you also tell the output, what the output should be. You give the input and you tell what the output should be. With this, the computer start guessing, learning how this two input and output are related. Okay, in the presence of so many input labels and so many output labels, it will start guessing the function. Okay, right. So, so in short, I would like to tell you here is, for example, you give a set of points like this. Say you give a set of points. See, these are my data points. So how many? 1, 2, 3, 4, 5, 6. Some 6 data or 6 or 7 data points. Okay, I give 6 or 7 data points. Now, I will ask, what is this data point all about? Okay, so what do they tell you? Okay, and I have a new data point somewhere that I will introduce later. Okay, now the computer will look at this data and it will say, okay, I can say that it is like a straight line.
Sir, excuse me, sir.
Yeah. Yes, ma'am.
Your screen is not visible, sir.
Not visible?
Screen is not visible.
Okay.
Yeah.
Okay. I'll just press it. Innocent tell that. Is it okay now?
Sir, okay, sir.
Yeah. Okay.
Sir, visible.
So if you have any problem, just interrupt me. Okay, no problem. Okay. I don't know why it is going on like that. Okay. Okay. Now you can see for whiteboard. Yeah. So here, now you ask this data point also. So it will say that okay. So this is actually A is actually delta y by delta x. So, okay, so I will say that the system will say, okay, this is my line. Okay, so these data points are represented by this line. Now suppose I get a future value. Okay, value which was not known to me before, but a future value. So the future value is, say for example, it is here. This line solution. Okay, because the future values, the future point is you got is this point, but the line is here, and here you can see that there is an error. This much is an error. So naturally, this is not your guess. Could this be? So this could be a nonlinear function. Okay, this could be a nonlinear function. So the nonlinear function can be something like this. Okay, so it is a polynomial of degree 3. Okay, so it is some ax cube plus x square plus dx plus. So this is my function. Okay, so initially I thought this was my function, but now I say that this is my function. Okay. So now you see that the future value is actually which was here is was function or whether this was the function, we still don't know. Okay, suppose in future you may get, say you can have a better, you can have another function. It could be a simple sine. This case you can have a sine wave. So that could be another function. Okay, so we do not know what is the function. So that's the problem with machine learning. We do not know what is the function. So it is, the function is a black box, but we have to guess the right function. Okay, and when you guess the right function, what is that we have to do is you can operate only within the limits of the data. You cannot describe the system completely with this because the model that you are trying to build with the machine learning is called empirical model. So empirical models are based on data. So with whatever data you have, you can describe the system, so that empirical models can be used only for prediction. As a whole. So this is not possible. So only I think I can do is prediction. Okay. So that is what actually machine learning is all about. So in my case, what I am going to do here is my model will work only in this range. This range. If I give a new point, but range, and in this range, it is not understood. Okay, how the system will behave is not understood. Provided you had data, because data is always limited. Okay, available data model, and we can call that model empirical model, and within the bounds of that model, within the bounds of those data, I can do a prediction, but I cannot describe the system as a whole. Okay, so that is all about. I'll just this is all about machine learning. Okay, so these are the different types of learning algorithms. So as I told you, labels. Unsupervised learning, which you generally call clustering. You are given only with the training data. You are not given labels. You are not explicitly given the labels. Sometimes your data may have training data with partial labeling. So in that case, it is semi-supervised. Sometimes it may not be possible to give you data. Okay, you have to know only whether you are right or wrong only after you have taken some certain number of steps. Okay, especially with, say, for example, playing chess, when you are making the computer play chess. So in the chess game, so you do not know how each move of the user you cannot say whether it is right or wrong. Okay, you cannot label each move of the each move of the till the end of that, whether the move that you have made led you to win the game, or you really did a checkmate of your opponent, or whether the opponent checkmated your king. So you know only at the end that whether you are right or wrong. Okay, so that is you learn by rewards and penalties. Suppose then, and that is a reward, and that is reinforce your move. If you have made some moves and you have lost, in that case, that's a punishment. So in that case, again you learn that those are not the right moves. At the end, you know about wrong. So such applications are called reinforcement learning. Especially where you can take the example of a taxi driver, who's driving a taxi with a passenger. Because nowadays you know that because machines are going to take the taxi, no drivers, we are going to have driverless taxi. So the driverless taxi is taking the passenger. So in that case, on the route, suppose you cannot tell whether each and every move the taxi makes whether it's right or wrong. Okay. So only at the end when the you take him before time comfortably, in that case he will give you a tip. So based on the tip, it's a reward, and you know that you have done a good job. Okay. Suppose you are not, you took him late airport. On the way, you made a lot of sudden braking and other things. The passenger was not comfortable, or you met with some minor accident. So in that case, the taxi, the passenger will not give you a tip. Okay. So, or nowadays you know it is all about this Uber and Ola. So they will not give you rating. Okay, star rating. So in that case, you can understand that you have done a bad job. Okay. So those comes under reinforcement learning, or reward for sequence of action. Okay. So these are the different types, and of course, but actually network. I think my presentation is getting disrupted, no? Disturbed. So deep learning is actually about neural networks. Okay. With deep hidden layers. Okay. So in deep learning we employ different types of learning. Okay. So that will get. Next is a history of development. Okay. So that has happened. This you can just have a look at it. So you know that, as I told you, in 1960s onwards, so you have this concept of neural network. Okay. That pattern recognition and learning in the limit theory. Then as data bias net learning developments that happened, and then in 2000, in 2000, you have the SVM and kernel method statistical learning they came up, and 2010, you know that we now talk about deep learning and convolutional neural network and generative adversarial network GAN. Okay, so this is the development that has happened. Okay, since 1960. Okay, now we come to the role of mathematics. Why mathematics is necessary? What is the role of mathematics in machine learning? Okay. So you know that algebra. Then you have single variable, multivariable calculus, gradient, that is gradient based optimization. Okay, basic probability theory. So these are some of the core ideas in mathematics that are used heavily in our machine learning. Okay. So without this, we cannot have algorithms. Okay. So to understand the algorithms or to algorithms, have some understanding about this core concept. Okay. Now next we will, so as I told you, now we will get into the topic. The first topic is about vectors. Okay. So what is a vector? Okay. So we start. So because we have to, we start. So this is the basic component of linear algebra, the vector. So vectors are used in our machine learning applications heavily. Okay. So our data is actually represented in the form of a vector. So if you take natural language processing, we represent words as vectors. Okay. So only thing is that how you are going to represent your the entities in the natural language processing as a mathematical tool. Okay. So the mathematical world, the entities of processing or image as vectors. Okay. So what is a vector? Okay. So this is actually a vector. Okay. Vector is just as is a tuple. It's a tuple of which actually belongs to Rn. So what do you mean by say R of n is say if the tuple by say is a vector. Now x is actually some consists of some component x1, x2 up to xn, some components. Okay, where x1, x2, x1 they are components. Okay, and these components are real values. These components are real values. When I say R, it means real value. We don't know. Okay, in machine learning we are only dealing with real numbers. Okay, so we take we are going to deal with vectors in the real space. Okay, a real world. Sorry, in the real space, not in the complex space. Okay, and when I say Rn, so it's a tuple. Okay, so this is a tuple of n elements. Okay, n number of elements. So it is the so where n is the dimension. So we'll come to that. Okay, so where each field is supposed to be a real number. We are going to have. Okay, so it is an n-dimensional real coordinate vector or simply vector. Okay. So I think you know that. So we have been talking about vectors from your school days onwards. So you know what are vectors. So you know that we have been taught that vectors are actually uh, arrows. You have a vector. So vectors are really actually represented with arrows. You know that this is vector A, and you have another vector. You have vector A and vector B. Now, how do you say? Now, with this vector, so you know that vector has both magnitude. Okay, the magnitude is C modulus magnitude, and here the magnitude is A modulus. So vectors have the direction. Okay, so this vector is pointing this way and this vector is pointing this way. So vectors have both magnitude and direction. So that's what we are taught, and we know that the vectors are represented by arrows. Okay, and now to add two vectors, you know what to do. You have to bring this vector here. Okay, suppose I want to add A and B. Just put like this. This is vector A, and this is vector B, and then what you do is you create a new vector from this to this. Okay, and this is A plus 2. Okay, so this is how you do vector addition. This is how you do vector subtraction, all those things. So you know all this. Okay, right. Now suppose I want to elongate this vector. Okay, so what I do, I multiply this vector by a scalar. So scalar is just a real number. Okay, so what I scalar small a, new vector A A times A times A times B. So the vector will be scaled. Okay, when you multiply a vector with a number, the vector is scaled. If A is supposed to be less than 1, then the vector will be shrink. You will shrink the vector. You can elongate the vector, you can shrink the vector with by multiplying a vector by a scalar. Okay, and this is vector addition. Vector addition. So like this different operations. So you know this operation. Okay. So for example, so if I say in a two-dimensional plane, if I say there are two parts, say here in this example, I gave you a vector example which is two-dimensional. So we have only two things. So this is x1 and x2. So actually, to understand vectors even better way, so actually what you have to do is you have to see this thing as like this. So you have to see this is the vector. Now you have, what is this? This is x1, 2. Okay, and so this is capital X1 and this is capital X2. That okay. So now you know that. So what is this vector? Okay, so or I will take this vector from the origin. Okay, so for the initial time being, so don't confuse you. So we'll take the vector from the origin. So we'll take a vector from the origin. Okay. Now you know that I told you that it has a modulus, the magnitude x and the direction, and the direction is measured by the angle. You can also take the angle as the measurement. Okay. Right. Now this vector can be represented in your as like this. So it has two components. Okay, it has two components. This is the x component of the vector. X component, and this is the x2 component. I call this x and x1 and y. Okay, so this is x component, x1 component, and this is x2 component. So I can now represent this vector as x1 comma x2. Suppose you have 3 dimension. In that case, I can represent it as x1 comma x2 comma x2. But you can go for higher dimensions also, but we cannot visualize them. Okay, you can visualize up to 3 dimensions. You cannot visualize up to 3 dimensions. And I can say this vector is in a 2-dimensional space, but this vector is in a 3-dimensional space. Okay, and these are components of vectors along each axis. Okay, so what this is a vector x. Okay, this is the vector x, and this is the component of x in the x1 direction, and this is the component of x in the x2 direction. Okay, so that's what actually these two are components. Okay, these two are components, and what you have to learn is these two are called axis or basis. We call it as call them as basis. Okay, the capital X1 and capital X2 they are basis, and we are going to measure our vector against the basis. Okay, and say for example this is so our vector our vector x is a linear combination of two components, the a into x1 plus b into x2. So this is what our vector is. So this is how you visualize the vector. So far we have been visualizing a vector with an arrow, but now you can visualize a vector with in a coordinate space like this. Okay, in terms of their components. Okay, or sometimes I can also represent a vector in this component polar coordinate. So in which I can say that the magnitude of the vector and the angle. So that's the cos theta. So so this is cos theta. Okay, this is x cos theta, magnitude cos theta, and this is the magnitude sin theta. So I can either represent using Cartesian coordinates, or I can either represent the vector is the polar coordinates. Both are same. Okay, both are same. So just you have to keep in mind that the vector. Okay, so the representation of the vector can be done as a tuple. So I can say this 0, 1 is a vector. Okay, 2, 3 is a vector in two-dimensional space. Okay, these are vectors. Okay, instead of putting them in arrows, I just put them in this coordinate. Okay, so that's what actually you have to remember. Okay, so standard vectors are in this two-dimensional, three-dimension. So these are the axes. Okay, so you can see that this axis in a two-dimensional, this axis. Okay, this axis is 1, 0. Sorry, this axis is 1, 0, and this axis is 0, 1. Okay, now 0, 1 and 1, 0, these are the two axes. Now I can represent any vector as a linear combination of these two axes. That's all. For example, if I say a comma b is a vector, which I can write it as a into 1, 0 plus b into 0, 1. So in that case, what happens? A into 1, 0. So that is a into 1 is a, and this b into 0, 0, b into b into 1, 1 is 1. So you get a comma b. Okay. So I can represent a vector. So what about these two vectors? These two vectors, they are the basis vectors. These are the basis vectors. Now, if you have a 3-dimension, in the 3-dimension, the vector would look like this. Okay, this is the 3-dimension. Okay, 3 basis vectors. Similarly, n basis vectors. Right. So I can have n number of bases or n number of dimensions. Now, what is the algebra with vectors? Okay, just like you have algebra with numbers, you can have algebra with vectors. You can add vectors. Okay, I told you an example of adding vectors with a arrow. Okay, but actually addition of vectors happens with the component wise addition. You have to add the component. Okay, two vectors are there. For example, 2, 1, 0. This is one vector. Another vector is 3, 7, 2 is another vector. Now suppose I want to add these two vectors, then you have to add component wise. 2 plus 3, 5. 1 plus 7, 8. This is 0. 0 plus 2, 2. So this is component wise addition. So this is how vectors are added. Okay. Now, now what is this? This is another thing, that is just multiplying two vectors. Okay. So when I multiply two vectors, this I will come to that later. Okay. So this and this are same. So I will come back later. And you know the magnitude of the vector. How to get the magnitude of the vector? So getting the magnitude of the vector is just square the components and add them. That's all. That's called the magnitude of the vector. Okay. And two vectors are said to be equal if their components are equal. Okay. And now I come to the dot product, a special kind of operation on vectors. Okay. So here, what do you mean by dot product? So I'll give you the when I talk about the dot product. So I'll just give you the geometric view of the dot product. So you have a vector. This is say a view. This is vector B, and this is vector say A. Now, what is dot product? A dot B equal to. Okay, what is this equal to? Now, what is that equal to mean? So, actually, what is the projection of A on B? So, this is this area is the projection of A on B. Okay, that is what is actually the dot product is all about. Okay, the projection of A on B. So, what is the projection of A on B? Suppose if this is angle theta between the angle between the two is theta. What is the projection of A on B? The projection of A on B will be A into B into cos of theta. Okay, so this is dot product. Okay, this is dot product. A dot B is equal to AB cos theta. Okay. Now suppose if theta equal to 0, in that case what it means, both A and B they are parallel. So in that case this angle is 0, that means this is B and similarly this is A. So in that case the angle is 0, therefore the complete A is projected onto B. But here you see that the projection is not complete. But here when the angle is 0, you see the complete projection is on B. Therefore, in that case, theta equal to 0, cos theta will be 1. This is 1. Therefore, dot product of A dot B is just A. Okay. Right. If the angle is 90, if angle is 90 degree, then what that case what happens? So this is B, and this is A, and this is the angle between 90. Now we take the dot product AB cos theta. So theta is 90. So when I put this on the theta is 90, this becomes 0. Okay. Then therefore the dot product is 0. That means in this case there is no projection. When you project A onto B, because A is perpendicular to B. Okay. A is perpendicular to B. There is no projection. There is no projection on B. Therefore A dot B is 0. Okay. So this is a special operation that we do in vectors. We call it dot product. Okay. So actually here how it is done is, say for example you have components. Say you have a component. Say for example you have a vector x which is having two components, x1 comma x2. You have y with components y1 y2. Now what is x dot y? Dot product of x dot y is equal to is x1 y1 plus x2 y2. Okay, so you may not remember this. So what you have to do is, in matrix notation you have to write. Okay, that is x dot y is equal to x transpose y. So what do you mean by x transpose? So generally in linear algebra, x you have to represent as a column vector. So this I should not represent like this. This is actually a transpose. So when I say x means x1, x2. When I say y, it means y1, y2. Now when I say x transpose, I have to convert the rows into columns. So that is x1, x2. This is x transpose. Okay. Then into y. Y is y1, y2. Like similar, there is no transpose. Now you do a matrix. So what is the order of this? This is 1 cross 2, because 1 row, 2 columns. What is this? 2 row, 1 column. So now can you multiply these two matrices? Yeah, because these two are equal, so you can multiply. So when you multiply, what will happen? x1 into y1 plus x2 into y2. So that's what you get. So these two are same. So in vector notation, if you want to take a dot product between x and y, then you have to represent it as like. Okay. So dot product is always a scalar. When you do a dot product, what the output you get is a number. It's a scalar. Okay. So x is a vector, y is a vector. If I take dot product between x and y, what I get a real number. I don't get a vector, I get a real number. Okay, I get a scalar as well. So that is what actually the dot product is all about. Okay, so this is dot product. And what is the cross product? So cross product is the reverse. For example, I want to take the cross product of these two. Then what I will do is, I will take say x cross product x into y. Cross product x into y is x into y transpose, which is equal to x is what? x1, x2. What is y? Y is y1, y2. Because this is transpose. I am taking y transpose. So now you just multiply. What do you get? This is 2 cross 1 matrix. This is 1 cross 2. So 1 and 1 you can multiply. Yeah. When you multiply, what you get? You get x1, y1, and x1, y2, x2, y1, x2, y2. You get a 2 cross 2 matrix. So when you do a cross product, you get a matrix as output. Okay. When you do a cross product between two vectors, you get a matrix as output. When you do a dot product between two vectors, you get a real number or a scalar as output. Okay. So these are the different interpretations of the product between two vectors. So we have seen how vectors are added, how vectors multiplied. You do a dot product. How vectors are multiplied in a cross product. Okay. How vectors are equal, and how do you find the norm of the vector? This is norm. Norm means the length of the vector. Okay. So these are the algebraic actions that you do on a algebraic operations that you do on a vector. Okay. Now we come to a very important concept of linear combination. Okay. So what is linear combination? Okay. So as I told you before that I told you, that you can write any vector v. Suppose you have two bases. Okay, this is one base, two axes. Okay, this is one axis, this is another axis. In a two-dimensional setting, this is one axis, this is another axis. In that case, I can write my vector v as a linear combination of these axes. Okay, so I can have innumerable number of vectors. For example, if you take say, for example, if you have something like this, say this is my axis. Okay, this is 1, 0. This is 0, 1. Okay, these are my axes. Now I can write any number of create any number of vectors. For example, this vector. So this is some number, say C1. And this is some number C2. So it will be C1 times 1, 0 plus C2 times 0, 1. Other vector I will draw. What is this? This is some number D1 and this is some number D2. So this is D1 into 1, 0 plus D2 into 0, 1. Okay. So what is the difference between this and this? So this means these two are bases. But whereas these two are vectors that have been created using the bases. So these two are linear combination of bases. I call them, they are the linear combination of bases. Okay. But if you take the bases are independent. Say I cannot represent this vector using this vector. I cannot represent 0, 1, 0 with 0, 1. I cannot express 1, 0 with 0, 1. Why? Because these two are perpendicular orthogonal. We call them with the name perpendicular. We say orthogonal. Okay, so it means they are perpendicular. So they cannot be expressed as one another. But whereas this vector, for example, I call this vector C and this vector I call it as D. But whereas C can be represented as linear combination of these two bases. Similarly, D can also be represented as a linear combination of these two. So that's what we call as linear combination. Okay, so that's called linear combination. So any vector can be written as this form. So in a 3-dimensional form and in n-dimensional form. Okay. So for example, now I'll say I come to the topic of linearly dependent, linearly independent. Okay. Suppose you take a set of vectors v1, v2 up to vn in a space which is Rn. Rn is actually a r-dimensional space. Now in a r-dimensional space, you take n vectors v1, v2, vn. are they linearly dependent or whether they are not linearly dependent. That's what our thing is. We want to know whether they are linearly independent or whether they are linearly dependent. That's what we want to know. So what does it mean to have linearly dependent? Means the vectors are linearly dependent if this is true, meaning there is some constant times v1 plus some constant times v2 plus some constant times vn. If we add them and if they are all equal to 0, given that c1, c2, cn are not 0. If c1, c2, cn are 0, then it is trivial. You know that it is not true. It is trivial. But if c1, c2, cn are not 0, but the linear combination of them, if you put them together and you find them equal to 0, then we say that these vectors are linearly dependent. What does it mean? It means that one vector can be expressed as combination of other vectors. Okay, for example, I'll just write it here. Say, for example, if I suppose there are vectors v1, v2, v3, vn, and I want to know whether it is linearly dependent or not. So in that case, what I will do, I will say v1, v1 plus v2, v2 plus vn, vn. If it is equal to 0, then where c1, c2, cn not equal to 0, then what I can do is I can just take this cn this side. So what will happen? c1, v1 plus c2, v2 plus cn minus 1, en minus 1 equal to minus, because I'm taking this side, so it is plus, so at that side it will become minus. So what is that I'm doing? And now bring cn this side, minus cn this side. So what will happen? It will become minus c1 cn into v1 minus c2 cn v2 plus like that plus cn minus 1, so not plus, so this is the minus also because of this minus cn minus 1 divided by cn into vn minus 1 equal to minus 1. So what I can do, you can see that I can represent any vector as a linear combination of rest of the vectors. Okay, so if any one of the vectors is able to, if I am able to represent as a linear combination of other vectors, then those set of vectors are not linear, those set of vectors are linearly dependent. We have to say that they are linearly dependent. If this condition is true, then we say that v1, v2, v3, vn are linearly dependent. Okay. But if this condition is not true, then we say these vectors are linearly independent. When vectors are linearly independent, we mean that these vectors, they are all orthogonal to each other. That's it. Okay. When vectors are perpendicular to each other, then we say that they are not linearly dependent or linearly independent. Okay. So this is the term that you have to remember. Okay. So when vectors are perpendicular to each other, pairwise perpendicular to each other, then we call them linearly independent. But if the vectors are not perpendicular to each other, then we can call them linearly dependent. In that case, whatever, this condition will be true. This condition will be true. So that is what actually you can just take this because of time I'm just running. Okay. So what is that relevance in ML? Okay. So we need to represent feature vectors as linear combination of a set of linearly independent vectors or orthogonal vectors. So generally in machine learning, we will be always talking about features. Okay. So we'll take for example a mobile phone. So what is a mobile phone? Mobile phone is having, say this is A is a mobile phone. The mobile phone is having some set of features. So what are those features? Say for example battery backup. Okay. Say the size of the screen. Okay, size of the screen. Battery backup, F2. say the something else, there's a camera, okay, so many features. So where S1, S2, these are features, okay, and we are representing our mobile phone A as a set of features, okay, and we see that these features are not dependent on each other, okay. So you see that the battery backup is independent of the screen size, okay, or the audio quality is independent of something else, okay. So you have to take distinct features, you have to take linearly independent features or orthogonal features, and you have to represent your vector mobile phone as well, okay. So that's why we are learning this. This is how a vector is mapped onto a this our objects in our machine learning, okay. Generally, what will happen is that you will have a lot of so depending upon the number of features, you will have number of dimensions, because when I have independent features, say I have 10 independent features, I have 10 dimensions, okay. I need 10 dimensions to represent my mobile phone or any of my objects. In that case, sometimes what may happen is one feature may be the same as another feature. For example, if you take a land, if you take land, your say real estate, you're doing this is land. Say now you see the length, land, width is a feature, length is a feature, breadth is a feature. Say area is also a feature you can take. You can take some other features like whether it is near a school, near airport, or so many things. So many features are there. But here, if you see the length and breadth, they are independent features, but area is not an independent feature. Area depends upon length and breadth. Okay. So in that case, this is what is called linear dependent. So they are linearly dependent. If I say this is linear dependent. Okay. They are not linearly independent. Area is not independent of length and breadth. Area is just length and breadth. That's all. Okay. So it depends upon length and breadth. Okay. So in that case, you can find some in this way you can find some features which are not which are dependent on something else. So in that case, you can just remove them. You can remove them, and we call them dimensional reduction. We call them dimensional reduction, which will come later in our course. Okay. So this is what a basis I told you. So this is one basis. This is another basis. Okay, for a 2-dimensional vector. And for a 3-dimensional vector, we have 3 bases. Okay, n-dimensional vector, n bases. Okay. See, matrix itself is a basis. See, we take a matrix. Matrix itself is a vector space. I can call matrix itself as a vector space. So it's a m cross n matrix. So I can see that these are the basis of different n cross 1 matrix. For example, if I have a matrix A, B, C, D, how to represent this? This can be represented as a linear combination of A into 1, 0, 0, 0 plus B into 0, 1, 0, 0 plus C into 0, 0, 1, 0 plus B into 0, 1, 0, 0, 0, 1. Okay, so 4 bases. 1, 2, 3, 4 bases, and just multiply them, add them, you get this. Okay. So generally, any standard basis, you can have any m cross n matrix as a basis. That can also be treated as a basis. So what is the dimensionality of R2? Dimension of R2 is 2. Dimensionality of Rn is n. Dimensionality of a matrix is m cross n. Okay. Dimensionality of a polynomial, nth power polynomial. For example, you have a polynomial an x power n plus bn, not an, a into b x power n, b into x power n minus 1 plus c into x power n minus 2, like that. You have up to some value. Okay. So that equal to 0. So it's a polynomial. Okay, nth power polynomial. It's an nth power polynomial. So in that case, these are coefficients of the polynomial. A, B, C are the coefficients of the polynomial. So in that case, for a nth power polynomial, what is the dimension of that? For example, if I write a simple one, I write in a quadratic term. Okay. Ax square plus bx plus c equals 0. Quadratic equation. So what is the dimension of this? Dimension of this is 3. It is n plus 1. Why? Because x square term, x term and a constant term. Constant term is t into x power 0 actually. So that's why it is x power 0 is 1, therefore t. So there are three coefficients a, b, c. So therefore the dimension of an nth polynomial is n plus 1. Similarly, if we take any polynomial space, then it is infinity, because a polynomial can have degree up to infinity. Okay, right? So where P is a set of all polynomials with coefficient from real. Okay, so dimensions of a vector space of a polynomial, they are infinite. Okay, so dimensions you can see, you can have infinite dimensions also. So now this is about finding the basis and other things. We can, I think I can skip them. Okay, because the time. Okay. Now I'll come to an important concept, that is about eigen value and eigen vector. Okay, so I think this concept is very important, because we need to know this concept very well. Okay, so you might have always seen about eigen values, but always learned about what is eigen value. Okay, and eigen vector. So what do you mean by that? Okay, so you know that now again I go back to the concept of vector space. Now vector space is this is my vector space, and say for example I have a vector, say vector here. Sorry, I will say I have a vector. Okay, so which has an angle theta and a magnitude, say I call it T. Now what I do, I use small e. Now what I do is, this is a vector small e. Okay. Now what I do is I want to apply some operations on the vector. On what operations can I apply on the vector? I can either increase or decrease the norm of the vector. The length of the vector I can increase or decrease, or I can rotate the vector in the two-dimensional space. Okay, I can change theta, or I can change the length. Okay, so these are the two operations I can do. Okay, and those operations are represented by matrix M. So a matrix M will be this. So when I apply a matrix M to A is a vector, then what do I get? I get another vector A dash. I get another vector A dash. For example, I want to rotate, say I want to rotate and shrink this one. So what I've done, I rotated this here, and that means I changed the angle from theta to alpha, and I have length also I have shrunk. Okay, it's not A, it's now some other value, say A dash. Okay. Now, so that is happening because of this matrix. Okay, this matrix is actually applied on this vector, and that matrix has rotated the vector and also scaled the vector. Okay. So in that case, so what will I do? Okay. Now, say for example, so this is actually any operation. Okay, any operation on a vector, okay, will result in either scaling the vector or rotating the vector. Okay, so you will change the direction of the vector, and also you will change the length of the vector through the operation. So that generally happens with any matrix operator on a vector. But there are some special vectors called eigenvectors for any matrix M. Okay, there for any operator, because I'm using the matrix as operator synonym. Okay, for any operator matrix M, there are some vectors which are eigenvectors. What happens is, those vectors you cannot change the direction. For example, the same M, if I am applying on an eigenvalue of M, for example, B is an eigenvector of M, B is an eigenvector of M, then I will get the same vector B, but scaling, it will be scaled. will not be, the direction of V will not change. Only the length of the V will be changed. It will be either shrinking or expanding, but I will not be changing the direction of V. So where lambda is a scalar. Okay. So here you see that if this condition happens, okay, when a vector is operated by a matrix operation, and as a result of that, the vector remains unchanged in the direction. In direction, it remains unchanged. Only thing is that only it is multiplied by a scalar. In that case, we call such operation as eigenpair. That means this vector is the eigenvector. And this lambda is the eigenvalue. So eigenvector and eigenvalue go in pair. So for lambda, there's a unique eigenvector. Okay. So if I take another lambda, another eigenvalue, lambda 2, I will have another vector V2, like that. So eigenvalues and eigenvectors, they go in pair. Okay. So now I think you understood that. So or I'll explain with that. I explain here. So here you see that, say for example, you have a vector. Now I multiply this vector A with a matrix M. So what happens is that as a result of that, the A is only elongated, but the direction stays. A small direction change is there, but no, actually it should be all right. Same direction. Okay, but only thing is it's now lambda times 2 because of the operation, because of the matrix operation on A. The direction has not changed. Okay, direction has not changed. Only thing is that the length of the length of the vector A has changed. So such operations are called eigenvectors and eigenvalues. Okay, so they are very, very important in our machine learning algorithm. Okay. Because those operations they do not change the direction of the vector. They only scale the vector. They only scale the vector. So this is the same thing. So it scales by the vector by an amount lambda. That's all. It does not change the direction of the vector. So generally, then there are so many other things. Okay. Suppose if two eigenvalues are not equal. Okay. Suppose if I have a matrix. Okay. For which there are two eigenvalues. And if the values are not equal, then we say that the corresponding eigenvectors, they are orthogonal. They are linearly independent. Only when the eigenvectors are linearly independent, then the corresponding eigenvalues will not be same. Suppose if two eigenvalues are same, then we get two vectors, and these two vectors, they are linearly dependent. Okay. Okay. So some of the eigenvalues can be got by adding the diagonal elements of the matrix A. Okay, some of the eigenvalues can be obtained by the trace of A. Trace of A means adding the diagonal elements of A. The product of the eigenvalues you can get, suppose there are two eigenvalues, lambda 1 plus lambda 2. Lambda 1 plus lambda 2 I can get by adding the diagonals of the matrix A. Similarly, if I want to find the product of eigenvalues, lambda 1 and lambda 2, then simply I have to take the determinant of the matrix A. That's all. So I get this. So these are only some properties that you can always find. So generally you can use these properties in our derivations of different algorithms for machine learning. Okay. Yeah. So this is the matrix, that is the M matrix I told you. M matrix I told you. This M matrix rotates a vector by an angle theta. Okay. So I was talking, so you have a matrix, you have a vector like this. I want to rotate this vector by an value theta. I want to rotate it by value theta. In that case, what is that operator? This is the operator. This is the operator that operates on any vector. Say, for example, the vector is x1, x2. I operate this with this vector, just a cos theta sin minus. So what is that you get? Anybody can tell me? Say, first line is x1 cos theta plus so minus, because minus x2 sin theta. Then second one is x1 sin theta plus x2 cos theta. So you get 2 things. Okay. So this, when you add this two things, this is the vector. So this is the initial vector x. So but when I operated this a vector with this thing, so what I got a rotation. I got a rotation of the vector in this direction. So this matrix, so this operator M rotates your vector. Okay. Suppose if we add a term A here, in addition to expanding it, it also scales it. So you will have A everywhere. So that means in addition to rotating the vector, it also scales the vector. Okay. Yeah. So here from this you can know what is the orthogonal matrix. An orthogonal matrix is one when all the columns are linearly independent. Okay. If you take a matrix, in a matrix, if the columns are linearly independent, or if their dot product is 0, pairwise dot product is 0, then we can say that such a matrix is called an orthogonal matrix. So when you have an orthogonal matrix, when you take the transpose of the orthogonal matrix, you get the inverse of the matrix. Okay. So that these are some of the properties that they are that one uses in our okay. And if you have a symmetric matrix is one which has n cross n, okay, equal number of rows and columns. If you have a symmetric matrix, then for symmetric matrix, and if the entries are real, then any symmetric matrix can be decomposed or can be factorized into three matrices like this. So if A is symmetric and real, then A can be written as product of three matrices P, D, P, where D is a diagonal matrix. Okay, and P transpose, they are the vectors, they are the eigenvectors. So what you will have is, for example, you will have this is P, then you have a diagonal matrix D, and the D will have lambda 1, lambda 2, okay, and this is P transpose. So what is that? Here you have a vector, two vectors you will have. These two vectors will be here. So any symmetric matrix A can be factorized into. So this is called diagonalization of a matrix. Okay. So this is applicable only when the matrix is symmetric, meaning n cross n. Okay. Yeah, symmetric means one more thing. Sorry, the upper and lower triangles are same. The upper and lower triangles are same. For example, this is the symmetric matrix. Okay. So like this, I can say. So this is one example. Okay, and next is. So these are again some of the properties. So if you take a orthogonal matrix, as I said before, the eigenvalues will be 1. That's all. You will have 1 as the eigenvalue. The determinant of an orthogonal matrix will be either +1 or -1. That's all. Okay. And the inverse of a orthogonal matrix will be a transpose. It's only when you take the transpose, you get the inverse. Okay. So these are some of the properties. Okay. Now we come to an important concept called singular value decomposition. Okay. So this singular value decomposition is is actually very much used in our machine learning. Okay, so I'll have to go extensively into this. So before that, I will just have a break. Okay, so because I've been talking for so many time, and so I think I need maybe the audience also needs some 2 minutes break. Okay, so I'll say I'll just break for 5 minutes and come back. Yeah. So I'm back. So in the meantime, just I would like to answer one. Actually, there's one query on the chat box which says which machine learning algorithm is suitable for robotics. So that I'll try to answer. So that is actually for robotics. Actually, when you talk about robotics, means what type of applications you are going to put the robotics. So that depends on that. For example, either you may go for reinforcement learning. Say, for example, if you are going to apply robotics for some job, okay. So, for example, now you find that no, the robots are used as bearers, okay, in cafeteria or hotel, okay. So in that case, suppose for such applications, if the robots are going to be employed, then for that you can use the reinforcement learning. So how the robot keeps the customers pleased, okay. So based on how fast it serves the food, okay, and all those things. So the customer satisfaction will give rating. Customer will give rating to the to the app, or he may give a tip. So based on that, you can see whether you're doing a good job or not, and based on that you can learn. Okay, so that is one thing. Or if you are doing putting robotics into some precision jobs, like for example cutting or something like that, in that case you can go for supervised learning. Okay, so that depends upon what type of application you are going to put your robotics in. Okay, so that's one thing. Okay. So now I think I can go back to my presentation. So we were discussing about this topic, that is singular value decomposition. Okay, we were discussing about eigenvalue, eigenvector, and then now we are going into singular value decomposition. So what is singular value decomposition? Okay. So I was telling you that if A is a symmetric matrix and it is real valued, okay, it is real valued n cross n symmetric matrix, square matrix, symmetric matrix. In that case, the symmetric matrix has is one where A is equal to A transpose. If A is equal to A transpose, then we say that the matrix is symmetric. Okay, and at the same time, the matrix should have real entries. Okay, real values. In that case, that matrix A can be factorized into three matrices like this. So matrix P, D, P transpose. Okay. So if A is symmetric, then A can be, like for example, it is like this. If A is a symmetric matrix, because only a square matrix can be symmetric, you cannot make a rectangular matrix symmetric. If you say a matrix is symmetric, then naturally it has to be a square matrix, n cross n. If A n cross n is a symmetric matrix, then it can be factorized into P, D, P transpose, where P is a matrix which consists of eigenvectors as columns. Eigenvectors of what? Eigenvectors of A transpose, A transpose. You just take A and A transpose, and then what you do is you just multiply them, then you get a no, sorry, not this. So for a singular matrix, it contains the eigenvectors of A. Okay, that is nothing but P. P is a matrix which contains as columns the eigenvectors of A into a diagonal matrix which has the eigenvalues in the diagonal. Suppose if it's an n cross n matrix, then you will have n number of eigenvalues, and these eigenvalues are in the diagonal. All other entries are 0. Okay, and then this matrix, this is P. This is P. Then you have another matrix, that is the transpose of P, which means the rows are the eigenvectors of A. Rows are the eigenvectors of A. So this is how you get. Okay. Now you see that what is that we are doing? From an arbitrary symmetric matrix, we are getting three matrices. So in which the middle one is a diagonal matrix which consists of the eigenvalues as the diagonal, and you have the first matrix P, which is the corresponding. So this lambda 1 is the eigenvalue of this vector V1, and lambda 2 is the eigenvalue of the second V2, like that. And this lambda 1, lambda 2, lambda n are in decreasing order. These values are in decreasing order. Lambda I is in decreasing order. Okay, and this is nothing but the transpose of P. So you get, so what is that you are getting? You are getting from an arbitrary axis, from an arbitrary basis, you are getting into orthogonal basis. So you know that since these are eigenvectors, V1, V2, Vn are eigenvectors, so they are going to be orthogonal to each other, pairwise orthogonal. V1 is orthogonal to V2, V2 is orthogonal to V3. So you take any pair of vectors, they are orthogonal. And this is the lambda is the eigenvalue, corresponding value. That means, for example, if you are having a basis like this, I'll explain with the diagram. Okay, you are having a basis like this. Okay, so we take two bases. Okay, arbitrary basis. Now, by doing a transformation like this, so what you get is you get a two axis. So this will be lambda 1, this will be lambda 2. Okay, two axes which are orthogonal to each other. These two are orthogonal, and one is scaled in this way by lambda 1, the other one is lambda 2. Okay, and this is B1 and this is B2. Okay, so this is what our matrix will be. So A will be, if this is A, when you transform A, you will get this. Okay, that wherein you have this two vectors V1, V2, which are eigenvectors of lambda 1, lambda 2 respectively, and this is going to be the V1, V2. Okay, so you see you get a transformation like this. Okay, so wherein you find that, suppose if we take that these are the two features. Okay, initial features are, say for example, A1, A2. Then now you see that these features are actually different. Okay, so you have a feature lambda 1 which is more important or dominant, then another feature lambda 2 which is not dominant. Okay, but here you do not know which is dominant or not. Okay, but when you go through a decomposition like this, so this is you get, and this is what you do in a symmetric case. Okay, provided A is symmetric matrix. Now suppose what about rectangular matrix? Can you generalize this? Can you generalize this for any matrix? So now suppose my matrix A is not n cross n, but it is m cross n, where m is not equal to n. M is not equal to n, and it is a rectangular matrix. So for a rectangular matrix, can I have a similar operation? Okay. Can I have a decomposition? Yes. That is what is called singular value decomposition. So that's what we have been. Okay. So suppose you have suppose you take any rectangular matrix A of m cross n. Okay, so it's a rectangular matrix. So there are m rows, n vectors, sorry, n columns. Okay, or I'll take number of rows as bigger. I'll take m as bigger. So it's a rectangular matrix. This is A. Now can I have a similar decomposition for this? Okay, so that is what is called singular value decomposition. So for that, what you have to do is, suppose you are given any A m cross n matrix. Okay, so what you have to do is you have to find A transpose A and A transpose. You have to find this two. Okay, you have to find this two. You have to find A transpose A and A transpose. So if A transpose A, what will you get? What will you get for A transpose A? What is the dimension of A? M cross n. So what is the dimension of A transpose? N cross m. A is m cross n. So when you multiply, what is the resultant matrix? Resultant matrix will have, what is the dimension? M and m will go away. So the resultant matrix will have n cross n. Okay. What is the dimension of this? A is m cross n. What is the dimension of A transpose? N cross m. Now again you see that n and n will go away. Therefore the resultant matrix will have m cross m. So you see that you get a square matrix now. Okay. By you find A transpose A or A transpose of this matrix. So you get two matrices. One is A transpose A, another is this. Now when you do a singular value decomposition of A, if I do a singular value decomposition of A, so what I get is I get three matrices U, sigma and V. I get three matrices U, sigma, V transpose. So what is this? So where U is a matrix, whose columns are eigenvectors of A transpose. So where U is a matrix, the columns of U are the eigenvectors of A transpose. Okay, what is the size of U? The size of U will be m cross n. Okay, what is sigma? Sigma is a diagonal matrix. Okay, with eigenvalues in the diagonal, in the decreasing order. All other things are 0. And what is U? This is sigma. What is V transpose? V transpose is a matrix whose columns are eigenvectors of A transpose B. A transpose B. Okay. So the columns of V transpose, this is V transpose. The columns of V transpose are the eigenvectors of A transpose A. The columns of U are the eigenvectors of A transpose. Okay. And what is the dimension of V transpose? It is n cross n. N cross n. Okay. Right. Are you getting it? And what is the dimension of this? This is the diagonal matrix. It is m cross n. M cross n. Okay. So this is the dimension. So you have m cross m U matrix. That sigma is m cross n. That is sigma. And the third one is V matrix. That is n cross n. V transpose. Now you find when you multiply them, you get the final resultant will be, so when you multiply this and this, what do you get? M cross n. When you multiply this and this, m cross n. Finally you will get m cross n. So that is what your A is. A is m cross n. So this is actually what is that you get. And this process is called singular value decomposition of any rectangular matrix. Okay. So, but whereas the previous case what you have studied is decompose, that is a single, that is a diagonal decomposition of a symmetric matrix. But here you can do it for any rectangular matrix. Okay, and you know that this singular value decomposition has so much of application in our machine learning, especially when it comes to dimensionality reduction. When it comes to dimensionality reduction, and of course principal component analysis. When it comes to principal component analysis, this is very much important. Okay, so just we'll see that. Okay, so for so these are the singular values. Okay, so the lambdas are the eigenvalues which are in the diagonal. You take the root of the diagonal, what you get is the singular value. They are called singular values. Okay, now yeah, this is what I was talking about. Okay, right. So U V transpose sigma. So V is a M cross N matrix, V is a N cross N matrix, and sigma is a M cross M matrix. Okay. So so this is actually about the singular value decomposition. And I already told you that in this singular value decomposition, these singular values in this matrix sigma, they are in the decreasing order. So you have lambda 1, lambda 2, lambda n. Okay. So lambda 1 will be greater than lambda 2, lambda 2 will be greater than lambda 3, like that, greater than or equal to, I should say. Okay, like that. So lambda n. So which means that the lambda 1 is a dominant eigenvalue. Lambda 1 is the dominant eigenvalue. The second dominant lambda value is lambda 2. The third one is lambda 3. That's what you get. Okay. So what is that application? Okay. So what is that application? Okay. So that application is of singular value decomposition is, so I'll just stop here. Okay. Say you just take this path. You just take this path, the upper one. You just consider the upper one. So this is a data. This is one vector, okay, which is in some basis, okay, like this, which you apply to a matrix A. A is an operator. A is an operator. When I say operator, I mean it is a matrix. Okay, A is an operator which applies on this particular vector. And when what it does, it not only changes the direction, not only changes the length of the vector, but also changes the direction of the vector. See, this vector has two perpendicular bases. Okay, so this basis I can call it x1, x2. But when it comes here, the basis itself has changed. Okay, the basis has changed to what? Sigma 1, sigma 2. Okay, sigma 1, sigma 2. Where sigma 1 is the square root of lambda 1, and sigma 2 is the square root of lambda 2. Singular value. And the vector has rotated. You see the vector has rotated. So you see that this sigma 2 is dominant. In this case, sigma 2 is dominant. Okay, its length is more, and sigma 1 is less dominant, the length is less. Okay. So this operator A has this effect on this particular vector. Now, the same thing I can simulate with my singular value decomposition. Now you forget this. Now what I do, I decompose A into these three parts. Okay. Now A becomes U sigma V transpose. Now I apply this on my vector some small v. I apply this on my some vector small v. Now what happens? You first apply V transpose to V. You first apply V transpose to V. So that's what we are applying. So first we have to apply V transpose to V. So star here means transpose. So first you apply V transpose to V. So that what it does, it simply rotates. It doesn't scale. It simply rotates. After that you apply sigma. When you apply sigma, sigma is what? Sigma is the eigenvalue. So that will scale. So sigma will scale. So you see scale. It applies scales sigma 1 and sigma 2. These are the scales that apply. Then finally, after applying sigma, now you apply u. When you apply u, again what happens? It again rotates back. It again does a rotation back. When it does a rotation back, you get this. Okay. So the same effect what you get using operator A on a set of vectors is the same effect you get by doing a singular value decomposition. Only is that this here we have this u is the what is that? U is the vectors, that is the eigenvectors of A transpose, and V is the eigenvectors of A transpose A, and sigma is the singular matrix. Okay, sigma is the singular matrix. Okay, so the same thing you will. So this is the geometric interpretation of singular value decomposition. Okay. Now, what is the say one beautiful thing about SPD is to find the inverse of a matrix. So you know that to find an inverse of a matrix, suppose A is a matrix. To find the inverse of a matrix, you need to find A inverse. You need to find A inverse. So how to find A inverse? So the first thing is that A should be square. Only for square matrix you have procedure or algorithm to find the inverse. You can find the inverse of a square matrix alone. But if the matrix A is a rectangular matrix, if A is m cross n, then I cannot find the inverse. Okay, it should be n cross n. Then only I can find the inverse. For a m cross n, how do I find the inverse? So you cannot find the inverse, but you can always find a pseudo inverse. You can always find a pseudo. Pseudo means it's not the real inverse, but actually a pseudo. I can find the pseudo inverse. So how do you find the pseudo inverse? So that's a small derivation. Okay, you know that A can be decomposed into U sigma V transpose. Now you take inverse of this. Okay, you take inverse of this. So when you take inverse of this, what happens? So A inverse is equal to inverse of this whole. Now when you open this, this is equal to so the inverse operation of V transpose will make it V. Okay, and sigma remains sigma because sigma is diagonal. So the inverse is same as this because diagonal matrix cannot, both are same. Inverse and the original matrix are same. Okay, and then about when you apply inverse to U, the U becomes U transpose. Okay, so that's what you get here. Okay, so now only thing is that this dimension has changed. Okay, m cross n, because now it has become n cross f. Okay, that's all. For example, an example is given here. So you have a 2 cross 3 matrix, 2 cross 3. So what do? You find the SPD. So after finding the SPD, this is U matrix, this is V transpose, and this is sigma. Okay. Now you take the inverse of this. When you take the inverse, just take the transpose of this and put it here. Okay. This is V transpose. So what you want is we want V. So take the transpose of this, put it here. Then this is just it is a 2 cross 3. You make the inverse will become 3 cross 2. The inverse will become 3 cross 2. And what is this? This is U transpose. So you take U, take the transpose and put it here. That's all. Now when you multiply this value, you get the inverse of the matrix. Okay. So which was not initially possible. Okay. So initially for finding the inverse of a matrix, you should have the matrix should be a square matrix. But here the constraint is not there. So here by using SPD, I can always find the pseudo inverse of any rectangular matrix. So another great application of this SPD is low rank approximation. It's what is called low rank approximation. So what is low rank approximation? So here we will take into consideration this example. Say I will go back to my so A is a m cross n matrix. Okay, which I do a singular value decomposition on that. So this gives me three matrices: U, which is M cross M, sigma, which is M cross N, and V transpose, which is N cross N. Okay, so this is what our application of SPD on this. Okay. Now you know what is sigma. Sigma is a M cross N matrix with say assume that M is less than N in that case. So you have now less number of rows and greater number more number of columns. So you will have some lambda 1, lambda 2, lambda 3. Other things will be 0. Okay. Now what I do is, now I find that the lambda 1 is a dominant vector, dominant eigenvalue. Okay. The value of this is, say, for example, 1.7. The value of this is, say, 1.1, and the value of this is, say, 0.001. Okay, our lambda. Now what I feel is these two eigenvalues, lambda 1, lambda 2, they are dominant, but whereas the third eigenvalue, lambda 3, which is having a very small value, so I can ignore that. So what I will do is, instead of making sigma as a M cross N, what I will do, I'll just make it 2 cross 2. So what I will do is, I'll just put lambda 1, 0, 0, lambda 2. Other things I have omitted. I have just taken this part. These things I am omitting. Okay. Because of that, now what is happening here? This, what is this? This U becomes M cross 2, because there are only 2 rows here, so it will be 2. Okay, or in general I'll call it R. If there are R number of rows here, I'll make it R. Okay, and this will become this will become B will become a 2 cross N. Okay, so or in general, what I will do is, I will by taking only R number of this N. R number of this M number of eigenvalues, I will take only small r. Say, for example, in that case, this value is R comma R. Okay, the sigma is R comma R. U is M comma R, M into R, and this V is V transpose is R cross N. So finally, my matrix will be A cap. A cap. This A cap will be M, RR will go away, and this RR will go away. Finally, my matrix will be M cross N only. I will have a M cross N matrix only. A cap will be M cross N, but whereas A is M cross N. But what is that I am doing? I am taking only rank R approximation. This is called rank R approximation. I am just taking only those dominant eigenvalues which are important to me. I feel that this eigenvalue 3 is, for example, you have n number of eigenvalues, lambda 1, lambda 2, lambda 3, up to lambda n. I may take up to lambda r. I may take only these eigenvalues. So I'll take a rank R approximation. Okay. So these values I say from lambda say lambda r plus 1 to lambda n. I don't consider because they are very small. So only these I take. So in that case, my A cap M cross N will be approximately equal to A of M cross N. They are not same because I have taken a lower rank approximation. So in that case, what is happening is, because of this, there are some latent variables which are coming into picture. So that is called, we generally apply them in latent semantic analysis as far as your NLP is concerned. In NLP is concerned, we apply this technique to something called latent semantic analysis, LSA. Okay, so in that case, you find that some hidden knowledge or hidden patterns emerge in A cap. They emerge in A cap, but they are not there in A. You cannot see them in A. Okay, so that is one thing. And another thing is in image processing. So that I will show you with an example. Yeah. So this is the same thing. So A is this. You just for simplicity, you are taken a M cross N. Actually, you can take any matrix. Okay. So you just convert it into this. So you get a, this is U matrix, this is sigma, this is D. Now you see that I ignore this value. I ignore this value. Therefore, I take only this. Okay, I take only this, and you see that when I take only this, so this is naturally becomes a 3 cross 3 from it becomes 3 cross 2 because only there are 2 rows. Okay, so this becomes 2 columns. Okay, I have to ignore this column. I just ignore this column. This column I just ignore. Okay, and similarly here I have to ignore simply this column. Okay, so now you see that when I done this, now you get this lower rank 2 approximation. This rank 2 approximation, which is because I taken only 2 values. So now just you compute this. Now you get A2. Now A2 is approximate, actually a rank 2 approximation of A. So A2 is rank 2 approximation of A. So you find that both are not same. You see, they are not same. So here you have item 0 here, 0, 0 here, but here you see there are some values are here. So what is those values? So those values are some hidden information or correlation. If you are talking about suppose in NLP, if you are talking about machine translation and other things, then we say that, say this is your French word and this is your English word. There is some connect, but in your corpus you find that there's no connection between this French word and that English word. But when you do a rank 2 approximation, you find that there's a correlation between this French word and that English word. Okay, like for example, Java is correlated to coffee. Okay, so you find that Java is a brand of coffee. Okay, so which may not appear in your corpus, but when you do a lower rank approximation, this evidence will come out. This evidence will come out, and that is what is called latent semantic analysis. Okay, and another example actually here I have shown is about this image process. Okay, so for example, this is your original image. Original, and here I'll go here. Okay, so I take a 10 rank approximation. I take a 10 rank approximation. So you find that, or I'll start from here. So I take a 25 rank approximation. Okay, so here you find that actual, so this is a complete set of eigenvalues. Complete set of eigenvalues is here, but I take only 25 eigenvalues, dominant 25 eigenvalues, and I deconstruct my image. So this is my deconstructed image, or I'll call this A cap. This is my original A. This is A cap. Okay, by taking dominant 25 eigenvalues. So in that case, you can see there's no much difference between these two figures. Do you see any difference? You see, this is the error. This is the error. So you see the error is very, very less, meaning that these eigenvalues which are here, they do not contribute to the image. Okay, so this leads to a lot of compression. Okay, now you can see that you can achieve a very good rate of compression, but of course lossy compression, but still we can achieve a very good rate of lossy compression with just 25 eigenvectors. Now if you take only 10 dominant, you just remove this also, you just take only 10. Okay, you take just 10, you just see here, you take only 10. In that case, you see that still, see the image is, you can see the image but little blurred, but you see the error which is somewhat more here. Okay, somewhat more. Now I go to the previous slide. Now here you say that I take only one approximation, I take only one eigenvalue, and that one eigenvalue gives me an approximation like this. So there a lot of errors are there, but because I have taken only one eigenvalue and the remaining all other eigenvalues I have discarded, I get this image as my reconstructed image. Okay, right. And here I take only 4 eigenvalues. Here I take only 4 eigenvalues, and the rest I discard. You see, I get a somewhat better image than this image. Okay. So this is the application of singular value decomposition. Okay. Now next topic that I would like to discuss now is actually, I think it is almost 15 minutes are there. So I'll just give you an introduction to this. Maybe in the afternoon I'll continue, then I'll continue with the rest of the topics. Is about the principal component analysis, PCA. PCA means the principal component analysis. So just to let you know what is the principal component analysis is all about and how it is connected to our SVD. Okay, so for this I will take you to my board. So here you see say for example you have a say you have a 2-dimensional data. Okay, so I will call it x1, x2, and the data is here. And data is here. Okay. Now, what is the variation in x1? The variation in x1 is this much. This is my variation in x1. Variance in x1. What is my variance in x2? This is my variance in x2. Where x1 and x2 are 2 features. x1 and x2 are 2 features. Now you feel that both the features are having equal variance, a large variance. Therefore, you will feel that both the features are important. Both the features are important. But what I will do is, I will simply take a SVD of this. Okay, I just take the singular value decomposition of this, and as a result, what I get is I get 2 different axes now. I get 2 different axes, which I draw with a different color. This is sigma 1. This is sigma 2. 2 different axes. Now you find that the variation among sigma 1, is large. This is the variation among sigma 1. But what is the variation among sigma 2? This variation, small variation. So this small variation in sigma 2. Okay. So that means sigma 1 is dominant and sigma 2 is not dominant. Maybe sigma 2 is noise. Okay. So you may find that this is noise, but whereas this is your data, but the variation in sigma 2 is noise, whereas variation in sigma 1 is what is needed. So from that, what you can do is you can ignore sigma 2, okay, and you can just work with sigma 1. Okay, only one feature. So from 2 features, we have reduced to only 1 feature. So that is what is called principal component analysis. Okay, so that's what actually is all about principal component analysis. So here you see that I have some points, okay, and this is the axis. Okay, this is the axis of this point. Okay, so there are 2 points. 2 axes, x1, x2. Now what you do is you take a say I take a mean of them. I take the mean of x and y. Okay, I want to get a mean 0. I want to remove the mean. I want to make it mean 0. So in that case, I take the mean. I take the mean average of x and compute x minus x bar. Similarly, I take the mean of y and I compute x minus y bar. Sorry, y minus y bar. Then I get this value. So this is y minus, this is x minus x bar, where x bar is mean of x, and this is y minus y bar, that is mean of y. So now what I mean is I have removed the mean, so it's zero mean. My mean is now removed, so zero mean. So now instead of data like this, I get the data like this, because now you see the mean is zero. Okay, my mean is zero. So my mean is zero. But here the mean is not zero. The mean is somewhere here. Okay, so it's not zero. Now after making it zero mean, I find the covariance. You know what's the covariance? I find the covariance matrix. I find the covariance matrix. After finding the covariance matrix, then I find the eigenvalues and eigenvectors. I go through this problem of SVD, and I find eigenvalues and eigenvectors. Now I have two eigenvectors. This is one eigenvector, and this is another eigenvector, and two eigenvalues. This one, this is dominant. This is dominant. Now after having these two eigenvalues, now what I do, I reconstruct x and y on this axis. Now I take these are my new axis. On this basis, new basis, I say V1 and V2. I use this dominant eigenvalues, and when I plot them, you find that this data is now, see, this data is now dispersed in this manner. This is U1, but whereas this dispersion among U2, this dispersion is not there. That has been removed. Okay, so all the data is actually variance is only on the U1 side, but on the U2 side, there's no variance. U2 I have eliminated. Okay. So because of that, now you see that instead of having two dimensions, now I have only one dimension. So one feature. I have only one feature. I can ignore the feature U2. So this enables our machine learning algorithms to save time. Okay, because instead of having two features, now I have to work with only one feature. Okay, right. So I think so with this I can stop now. Okay, because the time is up. So if any questions are there, I can take the questions. Okay. Yeah, questions. I find some questions. How to find the covariance matrix? Okay. So covariance matrix is actually very simple. Actually, you should know what is covariance. Say, for example, there are two variables. X and y. Okay. If I do x minus x bar, it is variance. X minus x bar whole square is variance. But if I do x minus x bar into y minus y bar, it is covariance. So covariance matrix will be something like this. So here you will find sigma x, sigma y. That is variance of x, variance of y. Because this is x, x, y, y. So for xx, this is the variance. For yy, this is the variance. But for x and y, this is the covariance of x and y. And naturally, it will be symmetric, because covariance of xy will be equal to covariance of yx. So it will be symmetric. So this is the covariance matrix. So finding the covariance is this: x minus x bar minus y into y minus y bar. Y bar is the mean of y, x bar is the mean of x. Okay. Whereas if you do x minus x bar square, it is variance of x. If I do y minus y bar whole square, it is variance of y. But whereas this one is variance of x comma y. Any other question?
Thank you, sir. I think no questions from the participants.
Okay, madam. Thank you so much for this session. So
Okay, sir.
let us meet again at 2 o'clock. Okay. Thank you.
Okay, sir. Thank you, sir. So, dear participants, the feedback link is available in the chat window. Kindly all are asked to give your feedback. Thank you.